Alright, so we just talk about conductivity today. Now, when you talk about conductivity, okay, and when you talk about electrochemical cell, like I have two electrodes and these are connected, okay. And there is a solution, let's say, okay. And we actually already said that there are many conditions that affect it. One is, of course, like how the electrons are flowing, right? But more important is basically how the ions are flowing. Okay. Now there is a big difference. We'll first give you a quick review of the electron thing, which you already know. Okay. Like Ohm's law and everything. But then why ions are different? Because ions are actually massive, and different ions can have different masses. Okay. So like cation can move slowly than the anion and vice versa. Okay. So what will happen due to this movement? Okay. That we are going to basically formulate. Okay. And how basically the conductance of a cell, okay, will be dependent on that. We'll actually define what is conductance. Now for I'm just using for this portion, okay, you can just read Haslam's book. There's a beautiful discussion here. You can also read Atkins, okay, but Atkins, I think the discussion is very brief, okay. Alright, the best discussion for this chapter is in Gladstone's book. It is a very old book. Samuel Gladstone. I mean, either his physical chemistry or there is electrochemistry book also by Gladstone. But again, the notations are different in Gladstone. Okay. All right. So the first thing first, let us define a quantity which is known as current density. Okay. Now. There are different forms of Ohm's law. What we study is basically the current, the potential drop. Okay, is proportional to the current is proportional to the potential drop. Okay, and then the proportionality constant is the resistance. Okay. But here we just took a slightly different approach. This is also Ohm's law. Okay, and basically it says that the current density is proportional to a gradient. Okay, now. The question is, suppose, think about a very simple thing. Let's say diffusion. We'll talk about it. Okay. Now diffusion will happen. Diffusion is what? It is basically migration of masses, right? Now mass will move from one side to another side if there is a concentration gradient. Okay. So we always talk about some quantity which has a gradient in space. That we can take as x or z, whatever. Okay. Some quantity, like suppose the concentration. If we have a flat profile in the concentration, there will be no net flow of mass. Okay. But if we have the concentration is changing like this, okay, then only we'll have a flow. Second thing, if you think about it, this mass, okay, actually move in this direction from high concentration to low concentration. Okay. However, the gradient, which means actually necessarily the slope, how this is changing, right? That is negative here. Okay, so we'll talk about it when we discuss diffusion. So similar thing is also here. Okay, now current density means how many electrons are flowing. Okay, per unit time, per unit area. Okay, now that will be proportional to a potential gradient. Okay, you know that any current flow actually happens because of potential gradient. Okay. Now, potential gradient means I can write del phi del x, but if it is just a one-dimensional problem, I can write d phi dx. Okay. And then there will be some constant if I just write it. Okay. Now, the question is if I write it in the d phi dx way. Okay. Think about it. When I am going in the positive direction, okay, this is the positive direction, I actually have a negative slope. So d phi dx is basically negative. Okay, so this can be concentration, this can be potential. If this is concentration, we talk about diffusion. If this is potential, we are talking about now electrical current flow, right? Charge flow, which is current. Now the question is, to make it consistent, okay, we always use a minus sign, so that minus d phi dx is positive. Okay, and the proportionality constant in this case we call as kappa. Kappa is known as conductivity. Right? So this is nothing but conductivity, right? And already you know that what is the negative gradient of potential? It's electric field. Okay, is by definition. Okay. So electric field is negative gradient of potential. So this is nothing but kappa into E. Okay. So E is basically electric field. Right. Now, okay. Now this is actually Ohm's law in a different way. Okay, but then we can actually write it like, say for example, if we write J is the current density. Okay. Now usually we write Ohm's law in terms of electrical current, right? So current density means actually how much charge is flowing per unit area per unit time. I just need the current means actually how much charge is flowing per unit time, right? So I have to just multiply by the area. So which means suppose if I have a conductor, okay, which has some cross-sectional area, let's say A, okay, and the length is something like say L, okay, then I can actually write this d phi dx, okay, this d phi, okay. I can approximate that this is not a differential change, but this is something like say delta phi. Okay, which is delta phi? Delta phi is basically the potential difference between these 2 points. Okay, and then I can also approximate that this E, okay, will be basically gradient of the potential, negative gradient of the potential. Okay, I am writing it just a minute. Basically writing minus d phi as delta phi. I can always choose that. Okay. And then the E is nothing but delta phi by L. Okay, this is just a gradient. Okay, but again, I'm basically switching from differential notation to finite notation, but this is valid if the gradient is uniform. Okay, all right. Now, what will be then my current? What is I? Let me first write the delta phi. So delta phi is nothing but I have wrote it as E as delta phi. E is basically delta phi by L, right? And then how do I define the current? I with current density. So J times A, right? So what is J? J is basically my kappa into minus delta phi d phi dx. So I can write it as kappa, and minus delta phi delta x I can actually write as E. Right? So this is actually familiar to you. Okay. Alright. And then I can further write basically kappa. Instead of E, I can write it as delta phi by L. Okay. Now you see that what I have, okay. I have basically kappa, I have missing one A. Now this entire thing, kappa A L, that is basically a constant because kappa is the proportionality constant of the current density. Okay. If A is fixed, N is fixed, that is also a constant. Okay. That's what you studied mostly, this form. That if I have a potential difference delta phi, okay, the statement says basically the current flowing, okay, is proportional to the potential difference, right? I is basically proportional to this thing, okay. Now when you write it, you always write it as delta phi or some textbook like V2 minus V1 or VA minus V2, whatever, okay. And then they write I into R, the proportionality constant in the resistance. So whatever we have actually is inverse of resistance, right? Which is known as conductance. Okay. So this I'm just writing as conductance. Okay. Or I could have actually written this equation as delta phi is R into I, but R is basically the inverse of conductance, which is resistance. Okay. Clear? Okay. So just yeah, and then we can actually discuss the units in a minute. Okay. Just follow the same notation, and E I wrote as G to rho. Alternatively here, okay, just like we wrote as conductivity, we could have actually defined inverse of conductivity, which is known as resistivity. Okay. So you could have just written as like 1 over rho, something like that. Okay. And this is basically resistivity. Okay. Units. Okay. Let's start from here. So I, everybody knows, right? SI unit is ampere. Okay. Charge per unit time. Right? Now what will be the what is delta phi? It's a potential difference. Okay. Is volts. So what is R? R is basically volt per ampere. That is known as ohm, right? And then inverse of that, usually call it as a Siemens. Okay, ohm inverse. Okay. Similarly, like what will be the unit of kappa? This is basically volt per meter. Okay, this is ampere per meter square. Okay, so just one it down. So this is basically ampere per meter square, right? And it will be divided by volt per meter, right? Okay. That's basically electric field. It's volt per meter. So the unit of kappa, what it is coming? Ampere per volt meter, right? Alright. So that usually, okay, now you know what is the resistance unit? It's ohm, right? Ohm we wrote as volt per ampere, right? So you can see that volt per ampere is basically, this is ohm inverse. So you can write it as ohm inverse, meter inverse also. Okay. So these are the different quantities that we usually talk about, right? When we talk about electrical conductance, in the sense that electric charge is flowing. Okay, and what the charge carriers are electrons. You can also think in terms of volts, right? Now the same thing, okay, we are going to discuss for ions. What happens in solution? Okay, but just before going to that, we'll just discuss one very important concept, which is actually known as mobility. Okay. Now think about it. What we talked about conductance. Okay, we'll just current density. Okay. We'll just start with same notation. Okay. Now again, try to think about what is current density. Okay, so some of the electrons are flowing in this direction. Okay. Now current density basically tells you like how many electrons are moving per unit time, per unit area, right? So it must be proportional to the density, which means like if I take say this is suppose unit area, okay, say 1 meter square, something like that. Okay. So if it is 1 meter square, okay, and if I just take, okay, let's say per unit time it is moving say a distance v, but actually v should be the speed of electrons. Okay, so then the total volume the electrons sweep is basically v times 1 meter square, which is basically v. Okay, now that volume, how many electrons you have? If I just multiply by the density of electrons, then I will get the total number of electrons. So those many electrons actually passed through this surface. Okay, each electron is carrying a charge which is proportional to E, right? So then, by definition, my current density will be, okay, basically the density of electrons, which I am writing as N tilde, okay, times V. How V is coming? Actually, it is V times area divided by the area. That is the volume, right? and times actually E, right? So which is nothing but, if I just write it in this way, and then we also wrote that current density is nothing but kappa into E, right? We can actually equate these two, and then we get a expression for kappa. So kappa is basically NVE by capital E. Okay. So N is the density of electron, okay, V is the speed, then electric charge divided by E. Okay. Now think about it, what is kappa? Kappa is basically a proportionality constant, right? Now kappa all by itself, okay, should not depend on the velocity, right? Or basically should not depend on the electric field. Meaning, suppose this is a proportionality constant. If I just increase the electric field, my current density is changing. Okay. If I have a high electric field, which is proportional to the gradient, okay, potential gradient, I'll have actually more flux of electron. Okay. But then this is a proportionality constant. This should not depend on me. Okay. Now we see that actually this is proportionality E, 1 over E. Okay, but that should not have, which means actually within this, okay, I'll have something which is also dependent on E. Okay, now E is electric charge, this is fundamental. Density is also constant. The only thing is that velocity is a proportional thing. Okay, meaning if I have a gradient, okay, the velocity that is also linearly proportional to electric field. Okay, then I'll have a situation that that proportionality constants are actually cancelled, and then kappa is independent of the electric field. Clear? So somehow, okay, this V, okay, should be proportional to the electric field. Okay, electric field strength. And that proportionality constant, we call it as mobility. We write it as U. Okay. In this case, it is mobility of electrons, but we could actually talk mobility of ions, which we are going to introduce. Okay. So mobility is nothing but the velocity per unit electric field, because the velocity also should change. Okay. And if I just plug it here, it will be nothing but density, mobility times U. Now it is independent, okay, of the electric field strength. Now the question is, usually, okay, what will be the picture of the mobility? Picture of the mobility in the sense, suppose I have electrons, okay, which is moving through through a metal, let's say, okay, or conductor, right? Now usually when you write, think about it, the electrons as classical, okay. Then basically there is a force acting on the electrons, okay, some charge is moving. Now that force, think about it, okay, is basically I can think, right, some electric field is there, okay, if I just multiply it by the charge, I'll get the force, right? Now that force should equate basically the electron's motion, right? The electron's motion within, say, a metal, okay, what could be the motion thing? Which is, one is basically inertial force. What is meant by inertial force? Something like, which is initial velocity, something like Newton's law, okay, which is basically mass times acceleration. Okay, if I write it as mass, okay, times the acceleration, that is basically the inertial force, the speed with which electrons are moving. Okay, and then there should be some amount which is basically the frictional force, because if something moves in a medium, okay, you always have some frictional force. Okay, now the frictional force is proportional to velocity. You all know, right? Like pendular motion. So always we write that if I have a driven pendulum, right? So I have some motion of the pendular. How we write it? So d2x, dt2, or we can write it as dv dx. Okay. This is basically the inertial force. Okay. If there is no net force acting on the system, the particle will basically move with this, right? And then I have a frictional force. Now the frictional force, I can write it some constant into velocity. Some people write it as with the negative sign, because actually the friction actually acts in the opposite direction, but the sign can be included inside. It doesn't matter. Okay. So that I'm just writing. Okay. And that proportionality constant, okay, some people write it as F, some people write it as the standard notation is gamma. Okay. And those force is basically equivalent to the external force, if there is any external force. In this case, the external force is created by the electric field. I applied a potential difference. Okay. A negative gradient of the potential is equivalent to the electric field. and then if I multiply with the charge, I'll get basically the net force. Okay. Now this is basically the equation. Okay, equation of motion. But now think about it. If the velocity has to be proportional to E, right? This term will be very small. Okay. It is mostly dominated by this gamma into V. Okay, this is basically the frictional force. And then actually you can make an analogy. Okay. Now, what is the origin basically of this velocity being proportional to the electric field? Okay. Because if you apply more and more field, if you think about it, okay, there is an inertial force that is not changing. Okay. But then the electron is experiencing more and more friction as it's moving more. Okay. It's basically colliding with the ions in the crystal lattice. Okay, you can think that electron, there is basically some valence electrons which are in the conduction band, right? And then if I have electrons in the conduction band, left things are basically ions. So I have in the crystal lattice, okay, I basically have ions left, which are atoms minus electrons, right? And now these electrons are moving basically. Okay, and then they scatter with these ions. And that scattering basically gives rise to friction. Okay. And based on this model, there is a whole thing of electrical conductivity. Okay, which starts discussing about first the classical model. Okay, which is known as a Lorentz-Drude oscillator model. Okay, I'm not going into the details. Okay, and then talks about the limitation of the model. Okay, why the classical model is wrong. Then you can think about the particle in a box model, and then you can actually modify all those models. Okay, those actually explain electrical conductivity. Okay, we will not go into the details, but we will actually introduce a similar concept for ions, where I will also say the ions velocity, okay, will be actually can be replaced by something known as the mobility, okay, which is basically when the ions are moving per unit field gradient, okay, or sorry, potential gradient, or basically per unit field, okay. All right. So now let us talk about ions. Okay. Now again, just think about, let's say, electrolyte. Okay. But I'm writing it as the electrolyte as A nu plus D nu minus. Okay. So the charge on A, I'm assuming that it is Z plus, okay, and charge on B is basically Z minus. Okay. For example, let's say anything. Let's just take an example arbitrarily. Okay, say FeCl3. Okay. So nu plus here is 1. Okay, A is iron, B is chlorine, right? So nu plus is 1, nu minus is 3. Okay. So Z plus is basically plus 3, Z minus is minus 1. So always, of course, for electrical neutrality, I should have nu plus Z plus must be equal to, let me just write as Z plus this way, or maybe as a subscript. So nu plus Z plus must be equal to nu minus Z minus. Okay. That's the condition for electrical neutrality. Okay, clear? Alright. Now the question is, what is the current density for this species? Okay, in a very, very similar way. Okay. Now think about it. In this case, okay, so the cations are moving, suppose, in this direction. Okay. So the anions must be moving in the other direction. Right? Now the cations, which are the cations is basically A Z plus. Right? And the anions are basically B Z minus. Okay. Now think about it, when the cations are moving, okay, those are carrying positive charge towards it. Okay. Now if I write the current density only for the cations, I have to write how many cations are there. Okay, the number density of the cations in the same way. Like n times the velocity times electric field, something same way. Okay. But in this case, actually, I was carrying charge E, right? And in this case, it will be Z plus into E. Okay. Now that charge is being carried. For the anion, now, it is very interesting. So let me just write it first. Okay, so basically it will be carried by cations plus it will be carried by the anions, right? So for cations, I'll just write the same way. Okay, I'll just write it as N plus. So use the notation. Yeah. So I'm just writing the current density. I will write it as N tilde plus. Okay. And A and A will cancel. Then V plus. Okay. And then I have basically J plus into V. Right? So that is moving in this direction. For anions, actually these are moving in the other direction. Okay, but let me just write it in this way. I have say N minus. Of course, N plus and N minus will be different because it will depend on the stoichiometry. Okay. If nu plus and nu minus are same, then actually they are same. Okay, otherwise they are different. So for anions, I will have N minus. Okay. Now, if I take V plus as the positive direction, okay, I have to take the V minus as minus V minus because it is moving in the other direction. Okay. And then Z minus, but the charge is also not E, it is minus E because it is anion. Okay. So together I will see that these two negative things cancel. Okay. So it is as if cation plus anion together. Why it is happening? It is very simple to understand physically. Like I have positive thing moving, it is equivalent to negative thing moving in the other direction. Okay. So overall, there is a positive thing moving in this direction, which is contributed by both positive ions as well as negative ions moving in the other direction. Clear? Just like in conductors. Okay, you always say that the electron is moving, but you could have thought the same thing as holes are moving in the opposite direction. Here actually both things are moving, cations and both. Okay, because both are mobile. So I can actually write it as basically I have N tilde plus G plus J plus E plus B minus Z minus E. Clear? Alright. Now think about it like suppose I took the initial concentration of this compound as say something, let's say C tilde. Okay. Now what will be the N plus? N plus will be nothing but, it's basically say molar concentration. Let me just write it. This is molar concentration of this compound, okay, which is A mu plus B mu minus. Okay. So what is my N plus? N plus is basically total density. It's not a molar density because remember that was basically volume times the number density. Okay. So if I have this many moles, okay, if this is a stoichiometry, each mole will give me nu plus cation, right? So the number of moles of cation will be nu plus times C. Okay, those many moles. If I multiply by Avogadro number, then I'll get the number. Okay, so I can just write it. I can take something common. In both cases, as you can see, C will be common. Okay, because actually I'm going to replace this N plus, okay, as C times Avogadro number times my nu plus. Okay, now I'll be left with this Avogadro number times E. That is also common. That is nothing but F. Okay, so what I'm going to do is basically I have C and F, those will be common. Clear? And then inside I will have N plus I replace by C times Avogadro number, okay, times nu plus. So inside bracket I will have nu plus, V plus, J plus. E already I have taken inside F, okay. Plus I have nu minus, V minus, Z minus. Clear? Okay. Alright. So again, instead of like, yeah, so basically this is the formula for current density. Okay, so what is the formula for kappa? Kappa is nothing but J divided by E, right? If I have divided by E, okay, so V plus by E I can write it as U plus. And V minus by U I can write it as U minus. So the corresponding formula for the kappa will be C tilde F, okay. U plus Q plus, Z plus mu minus U minus Z minus. Okay. Clear? Alright. Now think about it. What usually, okay, I wrote the conductance there as L, right? Now that is usually preserved for electrical conductance. Okay. For electrolytic conductance, okay, we usually use the notation as lambda, the Latin equivalent of L, capital L. There actually we are writing capital L. So this is the same thing. Okay. This is the conductance, but in this case, this is actually ionic conductance. Okay. Now, what is ionic conductance? Ionic conductance, just in the same way, right? We had basically, if you remember, I had kappa, okay, and I am saying per unit concentration, what is basically the conductivity, okay. So that is defined as kappa, okay, divided by per unit, basically molar concentration. Okay. Now, if I have defined this thing, okay, so in terms of my equation, what it will be? It is just straightforward. So we just divide it by C tilde. Okay. So I'll just have F minus U plus U plus J plus minus sometimes it is also written as, okay, let me just show you. Okay. Now, as you can see here, what I have here, I have lambda, okay, which is kappa divided by C tilde, okay, which is basically F U plus Z plus whatever, okay. Now, think about it. If I just take, okay, if I just write it in this way, so this again, okay, will have a dimension of something like lambda, okay, because this is just a number, okay. So then this quantity, we call it as basically the contribution of lambda, which is ionic conductance, which is given by the cation. Okay. So we write it as something like mu plus lambda plus and mu minus lambda minus. Clear? So basically I have conductance. Okay. So this is the overall conductance. This is again the overall concentration. Okay. This is the overall kappa of the solution, which is contributed by both the cations as well as the anions. Okay. And I am basically dividing it into two parts. Okay. This is just a notation. Okay. Now, this treatment was done by Kohlrausch. Okay. And he basically said that whenever you talk about electrolytic solution, okay, you have to talk about both cations and anions. This is basically following the Arrhenius, this theory of electrolytic dissociation. Okay. Now, so far, the way we have drawn it, okay, we have not talked about what is the degree of dissociation, whether this is like for sodium chloride or FeCl3 or something like acetic acid, because acetic acid will not dissociate completely. Okay, so you can make a connection. We'll come to that. Okay, so how many cations are there? How many anions are there? That we can make a connection, and then actually we can measure the conductivity. Okay. Now the problem is that this formula, okay, so when people write it, this total conductance, I can write it as a conductance of cations and conductance of anions, okay, because these are two parts, okay. Right now it is kind of inseparable in the sense that what you will measure? You will measure the conductance, right? Now conductance is a physical quantity that we already discussed, right? That I can always measure, right? How do I measure it? So, like say ionic conductance, I can have basically two electrodes, okay, which are deep solutions, okay. And then I can make a cell where actually I can fill in the solution, okay. And then what I will have, I will basically measure the resistance. Not people usually do not measure the conductance. Okay. So it will be attached to something like resistor LPT. How do you measure? By Wheatstone bridge. Okay. So if I just attach a Wheatstone bridge here, I can actually measure the resistance. Okay. And from the resistance, it is basically the reciprocal of it is the conductance. Okay. That's how I can measure it. Okay. Now the thing is that measurement will always give me this thing. Okay. And then I have no clue what is lambda plus and lambda minus. Clear? So that will be a difficult thing to do. Okay. If I can actually solve it for individually, lambda plus or lambda minus. Okay. Now the second thing here is that think about this conductance. Okay. Now I told that as of now, okay, here, okay, so this is independent of actually concentration because this is by definition per unit concentration how many? Okay, what is basically the conductivity? Okay, but suppose I am doing the conductivity measurement, okay, and then what I did is basically I suppose use concentration of different, like say potassium chloride I'm taking, okay, and I'm taking different concentration, okay. Now this equation is telling me actually the conductance should be same, okay, but in practice it doesn't. Why? Because as I'm actually concentrating the sample, okay, the movement of the cation actually is influenced by the movement of the anions, right? Because all this derivation, whichever I did, okay, the cation anion speed are not influenced by each other. Clear? But at a very high concentrated solution, okay, if I have too many cations, basically what will happen? They will basically surround the anions and the anions are also surrounded by cations, okay. All these things will happen, okay. And then that will definitely affect the velocity, okay. So then, since everything is dependent on velocity, my conductance should change. So, in principle, this thing should hold when the cations and the anions have independent velocities. And that will happen if the solution is kind of infinitely diluted. Okay. So in other words, we usually write, instead of writing it in this form, we always write a notation which is like this, lambda infinity, okay, which is basically lambda plus infinity and lambda minus infinity. Okay. So these are basically the infinite dilution rate. Only that sense we can actually write that cations and anions are independently contributing. I can actually add them. Okay. Otherwise I cannot add them. Okay. I'll show you the experimental curves. Okay. But before that, let me tell you one more thing. Yeah, so we wrote it as so you can actually write it like this. This kappa, okay, is nothing but I wrote it as C plus this one. It is basically C tilde min plus lambda plus infinity. Now what is C tilde? C tilde is basically the molar concentration of the substance, right? So, which means actually C tilde plus into multiplied by nu plus is nothing but molar concentration of the cations. Okay. So which I could have written it as C tilde plus. Okay. Lambda plus. Let me just not write the infinite thing. That is basically for like ideal condition. Okay. But I'm just writing, just dropping the infinite thing. Okay. But of course, this thing will only hold for infinite thing. Okay. And then I can write it as C minus lambda minus. In general, I could have written it as kappa is nothing but all the species and their conductance, the summation. Okay. So this is basically a compact notation for what is known as Cold-Russell's law. Okay. Now the interesting thing here, as you can see, there are two things. One is basically I cleverly multiplied this B plus with C to get a C plus. Okay. Now that is basically Ci. Now suppose I have something else. Suppose I have say acetic acid or say some acid base. Okay. In water. Now what will happen here? All of you know that if I add KCl in water. Okay. So what are the species? So far we are considering like cation and anion, which is 1:1. So I have K plus, I have Cl minus. But water also does auto dissociation, right? So I always have H plus and OH minus. Actually the species is H2O plus, but I will write it as H plus. Okay. But then my carrier is actually 4, not just 2. Okay. So even if I am actually adding 1:1 electrolyte, okay, I should use a generalized equation. Okay. In the sense, like what I'm trying to say here is that if I have say, anything like KCl or NaCl, okay, I have to actually write it as something like this. Okay. Lambda H plus and then I have OH minus lambda H minus. Okay. Then I will have the cation and anion also. Okay. But this part actually I cannot ignore. Okay. Now usually some people actually write it as basically the conductivity of the water. Okay. Now that's why when you measure the conductivity of water, okay, the water has to be ultra pure. Okay, you always use basically deionized water. Because if it is ionized, ions are present, okay, that will itself show conductivity. Okay. Secondly, to get the actual values, you have to anyway use a dilute solution. Okay, because this equation holds only for the infinite dilution or in a very very dilute limit. Okay, so then if you actually try to fulfill both conditions, okay, your water has to be very ultra pure. Okay, now what usually people do is that you take the conductivity, okay, and you measure the water's conductivity separately. You take the subtraction, okay, K minus Kw. And that will be basically equivalent to the conductivity of contributed by the ions only. Okay. But again, this is not very correct because the presence of the ion can also increase or suppress the dissociation of water. Okay, I am assuming that the water dissociation is independent of the presence of the ion. Okay. So without ions, whatever I am measuring, the contribution of water is the same in presence of the ion, but that's not a correct thing. But people usually do it. Okay. And then the other thing is that we can always do basically the measurement of the conductance versus say concentration. Now for strong electrolytes, something like say potassium chloride or something like this, we get a more or less linear curve. Okay, now you can see that this actually decreases with concentration because as I'm increasing, okay. So what is happening is that there are more number of counter ions, okay, which are slowing down the mobility. Okay. So of course you cannot actually get an infinite dilution. You always try to fit with a nonlinear equation and try to extrapolate it to get the lambda infinity value. Okay. This is a typical thing for strong electrolyte. Okay, for weak electrolytes, actually we have a very different curve. For electrolyte, this will be very sharp dependence. Okay, why? Because you know, like if I actually increase the concentration, the degree of dissociation will be now less. Okay, so I'll have a very sharp fall, something like this. Okay, and usually we cannot extrapolate it. Okay, now that's the problem. Okay, now how do you tackle this problem? That's the question. Okay. So what I'm right now going to discuss is that for weak electrolyte, okay, how do I measure lambda infinity, or basically the infinite dilution limit conductivity? Okay, where I can actually get this additivity thing, cations plus anions. Okay. Now I can actually consider some, let's say acetic acid. Okay. Acetic acid usually I'm just writing it as HAC. So this is the acetate and this is the proton. Okay. Now HAC of course get dissociated with H plus and AC minus, right? And suppose the degree of dissociation is alpha. Okay. So if I have 1 mole here, okay, when it is dissociated, I will basically be left with 1 minus alpha. Okay. I have alpha here, I will have alpha here. Right? Okay. Because if the alpha mole gets dissociated, I will have alpha here. Right? And if I had basically C tilde concentration, I will have basically alpha C tilde, alpha C tilde. Clear? Okay. And usually, for any fixed temperature, of course, there will be an equilibrium. Okay? And the equilibrium constant, we can write it in terms of the degree of dissociation. Okay? And then you can easily see it is basically alpha squared, C squared, right? Divided by 1 minus alpha into C, 1 C will get cancelled. Okay? So I will basically get alpha squared C divided by 1 minus alpha. Okay? Now, there is an empirical relation in the sense like this curve, okay, as you can see here, okay. You can actually fit it, as I said that you can actually fit it with some standard nonlinear equation, okay. And you can think that this thing, which is basically for weak electrolytes, okay, can be approximated as lambda is something like the infinite value thing, okay, and then it basically decays, okay, as a function of square root of which, and then we can actually use a proportionality constant. But this is actually one type of form which actually acetic acid shows. Okay, maybe your formic acid or some other acid may show a completely different nonlinear form. Okay. Again, that's why it's called empirical fitting. Okay. Now, one can also kind of say, okay, so this degree of dissociation is actually equivalent to something like lambda divided by lambda infinity. Now this was basically suggested by Arrhenius. Okay. But he said, you can think of it like if the degree of dissociation is 1, okay, then my lambda is equal to lambda infinity, which makes sense. Now when the degree of dissociation will be 1, when actually I have infinite dilution. Okay. So that way if you think, okay, then actually in that limit actually it holds. Only for the, not only weak electrolyte, but in a very dilute condition. Okay. Because of course I know that this is a nonlinear function, but still I am actually trying to make it kind of linear. Okay. If I use that, okay, here, then what I'll get is some equilibrium constant. Okay, I'll basically write instead of alpha, I'll just write lambda by capital lambda again, lambda infinity. Okay, so it will be basically lambda squared by lambda infinity, something like that. It will be 1 minus lambda by lambda infinity. Okay, then I'm just basically dividing both sides, okay, numerator and denominator, by lambda infinity square. Okay, if we do that, okay. So what I will be having, I have the C tilde, okay, and then I have lambda square. I had lambda infinity square at the denominator, right here. It's basically lambda square by lambda infinity square. Here I'll have 1 minus lambda divided by lambda infinity, which I can write it as lambda infinity minus lambda divided by lambda. So that thing will get multiplied, so I'll have this. This is just after rearrangement. Clear? Okay. Alright. Now, the interesting thing here, actually, the question is, how will you get the extrapolated value? That was the initial problem, right? For weak electrolytes. Now, I can actually solve it. How? We can, instead of plotting the lambda versus C, okay, I could have actually rewrite this equation as this. So this is just another way of writing this equation. Okay, you can easily figure this out. What I did is basically I just took the 1 by lambda. Okay. And if I plot 1 by lambda versus this thing, okay, then I see that that is a straight line. Okay. I could have actually plotted that. And from that actually, if I measure the slope and the intercept, okay, I can easily get the equilibrium constant. And from the equilibrium constant, I know the degree of dissociation. That way, I can calculate the equilibrium constant. Okay. And the 1 by lambda is basically the intercept. 1 by lambda infinity. Okay. So I can actually plot different quantities. Okay. I could have, instead of plotting lambda versus C, I could have plotted these two quantities. Okay. And then actually I have negative slope. Okay. And then the intercept will give me basically 1 over lambda. That is one of the way one can do. Okay. And this is something you already know. Something like, say, for example, second order rates. Okay. You always plot 1 over A versus 1 over AC2. Okay. Similar concept actually. Okay. Instead of plotting it a nonlinear function, I can always get a linearized function and then do a linear fitting. Okay. But then I'm not plotting the same quantity. It's not concentration versus time, it's a reciprocal of concentration versus time. That way you can do it. Okay, or the logarithmic function, something like that. Okay. So that we convert it to a linear plot. Okay. Similar thing we can also do here. Okay. Alternatively, I'll show you that we can also could have actually used the cold rush law in a very, very interesting way. Okay. Now what we have is something like, say, for acetic acid, which is ACH. Okay. Now I know that that is contributed by what? That is contributed by cations and anions, right? Now I don't remember, it is basically nu plus into lambda plus. Now nu plus and nu minus all it is 1 here because it's just 1:1 electrolyte. Okay. So I have basically lambda plus. Okay. But plus is basically nothing but H plus here, right? And I have lambda minus, which is nothing but AC minus. Okay. And these are all I'm talking about, say, infinite dilution. Okay. Now there is an interesting thing. That suppose I have acetic acid and plus, say, something else, like say NaCl. Okay. So how we can write it? So lambda acetic acid. I was writing it as instead of ACH, you can write it as HAC. All in the infinite limit. Okay. So I can write it as lambda H plus. And for NaCl, okay. Suppose I took basically acetic acid along with NaCl. Okay, and both are sufficiently diluted so that I can write it as if it is infinite limit. Okay. Now there is a trick. The trick is that I want the acetic acid thing. Okay. Lambda NaCl I know. How? Because it's a strong electrolyte. The curve is not so nonlinear, so I can actually extrapolate and get that value. Okay. Now I know in that infinite limit, okay, definitely it is contributed by the cations and anions. Okay. So acetic acid is contributed by H plus AC minus, this is contributed by Na plus and this thing. Okay, Cl minus. Now what I am doing, I am now doing a very interesting thing. Look at it. This thing, if I add, this is nothing but basically conductance of HCl. That's a strong electrolyte. And these two if I add, that is sodium acetate. That is also strong electrolyte. Okay. So this is nothing but lambda infinite, okay, HCl plus lambda infinity of NaDC. Okay. Now I see this is strong electrolyte, this is strong electrolyte, this is also strong electrolyte. So I can actually go back and measure the weak electrolyte without measuring it. Clear? Okay. because everything is strong. So nothing, I will have basically the lambda infinity of acetic acid is nothing but I could have taken HCl, measured the infinite dilute concentration. I could have taken acetic acid, okay, measure the infinite dilute concentration, okay, and I'll just subtract from these values, okay, the infinite dilution conductance of NaCl, okay. But again, this is true for only 1:1 thing. Of course, if it is complicated, like we should have actually written nu plus, nu minus, okay. But then we'll have complication because otherwise the stoichiometry should match, okay. But this is one of the very interesting one. Okay, I don't need to actually measure the weak electrolyte. I'll just measure 3 strong electrolytes, which I can easily extrapolate, okay. And from that extrapolation, I'll get all these values, and those values combinations will give me this thing, okay. And this holds because the Kohlrausch's law was additive in the infinite dilution, not in the general, okay. And since this was additive, I can always break things, okay, and put it together, okay, in a separate. Clear? Now we just discuss the last piece, which is known as transport number or transference number. So basically the transport number, come back to what it is mean, okay. Or sometimes, mostly it is known as transference number. This is defined as the concentration, suppose, is K of a particular species, okay, and divided by basically kappa. And kappa already know that it is nothing but C. Yeah. So this is basically known as transport number. Okay. Now transport number of the Ka type. Okay. Suppose I have sodium chloride, potassium chloride, and all in water. Okay. So then I have many species here. Okay. So transport number of it, basically a particular ion, okay, is defined as, think about it. What is this C plus C into lambda? Okay. Sorry, this should be lambda. Now, what is this C into lambda? C into lambda is nothing but some measurement of conductance. Already we discussed, right? Now, this basically tells me what is the total solution, okay? And this is basically conductance contributed by that particular ion. So, transport number gives you a kind of fraction of the contribution of a particular ion towards the total conductance. Clear? Okay. Now it depends on many factors, as I said, like in the say sodium chloride. Okay. Now you cannot just say like which one is contributing more. It depends on many things, not only just concentration. Okay, because concentrations here are same. It's a 1:1 electrolyte. I have same number of sodium ions and same number of chloride ions. Okay. But what makes the difference is basically the mobility, which is velocity per unit potential gradient or unit field, right? So ultimately, actually, everything is limited by the how fast or how slow the cations or anions are moving. Okay. If it is a fast moving thing, then actually it will carry the charge more. Clear? Okay. So that is basically known as the transport number, which is basically the, if I have so many electrolytes, okay. So then the fraction of the charge, okay, carried by a particular species is known as transport number. Okay. Because I know that C times lambda is nothing but some kind of conductance. Okay. Now I can actually write an equation for transport number only for 1:1 electrolyte. Okay. Why? Because let's say suppose I have a cation transport number. Okay. Now cation, how do I write? T plus. Okay. So T plus will be nothing but, so this is what it is basically conductance ratios, right? So what will be T plus? Anybody? It will be nothing but say mu plus lambda plus divided by the total conductance. Similarly, if I write mu minus, right, it will be just minus 3. Okay. As I can see that t plus and t minus will be equal to 1. Okay, of course it makes sense because it's a fractional concept. Okay. But of course t plus and t minus in this case actually I took 1:1 electrode. Okay, electrode light. Now we could actually modify this equation a little bit in the sense that I could actually write it. Okay. Lambda plus and lambda minus I could have written as these things. Okay, already we derived all these equations, right? It's basically z plus into u minus u plus, right? So if I just write it, what I will have, it will be basically u plus z plus u plus, okay, and in the denominator I will have u plus z plus, okay, u plus and u minus z minus u minus, right? So now you see what I will have. Let's say just write it for cation. So u plus z plus u plus divided by u plus z plus u plus and out u minus z minus u plus. So, what is nu plus z plus? Nu plus is the stoichiometry, z plus is the charge. For electrical neutrality, this and this should be equal, right? So these three things are basically equal. Okay. So transport number is nothing but the ratio of the mobility to the total mobility. Okay. If we had taken the minus, it would be basically u minus divided by u plus by u minus. Okay. So transport number is directly connected to the mobility. So that's what I was telling, like fraction of the charge, okay, which is carried by the cation and anion is not dependent on their numbers. It is ultimately connected to the how they are fast. Okay. Of course, it depends on the number. Like say FeCl3. Okay. Even if the chlorines are slow. Okay. Suppose I do not know actually whether iron is slow and chlorine is slow. Most likely the Fe3 plus are slower. Okay. But suppose if Fe3 Cl minus are slower. Okay. They can still overcome because I have actually 3. Okay. So this will this will hold. Okay. I mean in a different case, basically when I have everything controlled by only mobility. Clear? Okay. Or the speed of the anions. Okay. And there is a very small discussion on conductivity titration, which everybody knows. Like if I actually do an acid-base titration based on conductance. Okay. So what will happen? Like if I just suppose I'm doing a titration. Okay. So suppose initially in a solution I have something. Let's say I have base. Okay. So the carrier is basically OH minus, right? And as I'm neutralizing, okay, what is happening? Basically the conductance should drop. Usually for strong electrolyte, we said that it's kind of linear. Okay, it won't be exactly so much linear. Okay. And then it will drop, and then if you add excess, right, then the acid will basically become the conductor. Okay. And then of course the slopes can be different because the contribution by the anions are different from the cations because OH minus and H plus mobilities are different. Okay. And this is basically if I do a titration, okay, this will be basically the equivalence point. At the equivalent point, actually I will have non-zero conductance. Why? Because neutral water also conducts. Okay. So there will be some residual conductance always. And that you always do. Okay, this conductometric titration. So there is some discussion on conductometric titration here also. Okay. And but just as a summary, okay, why this part is very important is why the mobility of the ions are so important. Again, this is a very like simplified model of ion conductance. Okay, it just takes into account that the velocities are independent again. Okay, which should be true. Okay, at the infinite dilution limit. Okay. And the second thing is that always remember that in many technological applications, for example, let's say lithium-ion battery. Okay, the major challenge right now is basically when you do this charging discharging cycle. Okay, what happens is that you have basically, this is solid state battery, right? And you have some layers, okay, and within the layers I actually have the lithium ions. So I actually pull out the lithium ions and then I again move it back. Okay, when I'm doing it, so lithium ions are basically intercalated inside the layers, right? Now there are two things. One is basically the mobility of the lithium ion. Okay, how fast and how slow I'm basically doing this charge and discharge. Okay, but every battery has a lifetime. The reason is when you are actually putting back the lithium ions, right? All the ions actually do not go back and perfectly sit. Okay, because when you move out something, like suppose I have a crystal. Okay, I have some lattice point. Okay, and now suppose from here I am moving the ions out. Okay, and when I am bringing them back, they may not fit into the same site. Okay, there may be some defective way of arrangement. Okay, and it will increase with the number of cycles. Okay, and that is one of the challenges. Okay, in current day lithium-ion battery technology. Okay, like how do you pack the ions when you are doing actually the discharging cycle? Okay, when the ions are basically coming back and fitting. Okay, and then basically the structure gets distorted. Okay, the intercalation is not doing very perfectly. Okay. So the mobility of the ions are very, very important in that sense. Secondly, which I did not discuss, due to this difference, like suppose I have like a Daniel cell, think about it. Okay. So one electrolyte is here. Okay. I have an electrode, I have another electrode here. Okay. Now if I connect it, okay, of course I will not see anything because I have to move the ions also, right? And to move the ions, what I do is that I actually connect it as something known as salt bridge, right? Now, interestingly, what a salt bridge does. Suppose if I do not have a salt bridge, okay, and what I am doing is that I suppose I have some kind of membrane across which the ions can transport. Okay. Now, what will happen? Suppose the cations, okay, which we wrote as A, mu plus whatever, okay. And suppose the anions are moving, they are moving, but they have different velocities. Suppose I have my mu plus and mu minus are same, like same number of cations and anions are present. Okay. But since their mobilities are different, okay, as the current is passing, maybe suppose the cations move faster. Okay. So what will happen? Actually, I will not have actually electrical neutrality in the solution. I will develop a potential across this barrier. This is known as liquid junction potential, right? So this is basically as if this is a liquid junction, and I am developing a potential in the solution. Okay, and if I keep on doing it, extracting the current, at a point will come, I have actually more cations here, more anions here, less anions here. Okay, then these extra cations will actually stop the new cations coming in. Okay, so what's happening? Oh. Anyway, so then that will basically reduce the flow. Clear? Okay. So in order to actually make this thing continuously happen, I have to actually remove the thing. Okay, or remove basically the potential difference. And that's why what we will do is use a basically known as something known as a salt bridge. Okay. What a salt bridge does? Salt bridge actually provide extra ions, right? Which are actually same for cations and anions, which basically have similar mobility. So then actually your original cation is not reaching there. It's basically original cation is reaching up to the salt bridge, and from the salt bridge some ions are going. Okay, so that it always maintains this electrical neutrality. So salt bridge basically removes the liquid junction potential. Okay, there is some discussion in Atkins' book also. Okay, and based on that, you can also develop something known as concentration cells. Okay, but actually you could have actually started with different concentrations. Okay, and then you can actually get some electricity out of those cells. So we did not discuss those things here. Okay.